second approximation. So in this second approximation, they observed that in the previous failure, they observed that. So when you see the VI characteristics, so the VI characteristics is going to raise only after certain voltage. So this shows that it is going to have some amount of opposition. So after that only it is getting the current is allowed. So opposition means if you are having a battery here, that is input battery, to this to oppose this input current, the current which is coming from this volt battery, there should be one more battery, then only that can oppose the current which is coming from the input. So they assume that, so as the silicon was showing 0.7 drop and germanium was showing 0.3 drop, what they assumed is the diode, it is having an inbuilt battery in it. It has an inbuilt battery in it. Along with that inbuilt battery, it is going to have, as usual, this is a diode. So this is the ideal diode, whatever we are having. So they now assume that there is a battery which is of 0.7 or 0.3 and an ideal diode. What is an ideal diode? From our previous case, ideal diode is, it is just a switch. Okay, they retained the previous previous idea, to that they improvised, and now they started checking this. So now first case was forward bias. When it was forward bias, so they are going to close the switch, and they started allowing the current to pass through this. So what they did is they are going to connect a battery. So this part is external biasing, we are doing it. This part is the equivalent circuit of the diode. This is the switch, this is the battery. Now they started allowing the current to flow. So they slowly increase the voltage in this battery. So when it was crossing 0.7, then they were able to see that the current was passing through the circuit. So from this they understood that yes, the diode is having an inbuilt battery which is going to oppose the flow of current which is coming from the supply. If the supply is least, or if the supply is less dominant compared to the inbuilt battery of the diode, then the battery of the diode will be dominating, such that the current will be in the direction of the diode. So that's why what they came to know, yes, we need to give a battery which is always greater than 0.7. But this is fine. But when it comes to reverse bias, so it is reverse bias. If you pass current also, will the current pass through this?
No, sir.
No, because the switch is open. Okay, so they retained the same original idea. So even though you have a battery, but since for the current to flow through, it needs a closed path. Always current needs a closed path to pass through the circuit. But voltage can exist between any two ends, any two open ends. The voltage can exist, but to current to pass through, it needs a closed path. So here, since the switch is open, so there the current is not going to flow. So in the second approximation, they came with a graph which was, so I told you in the negative side, that is minus V, this is the positive side, this is IF positive, this is the reverse. So there is no current, so they assume for whatever negative voltage, that is reverse voltage you supply, the current will be zero. But in the positive side, when your input voltage becomes greater than 0.7, then the current starts increasing. And the current starts increasing. Now they again compared this curve with the actual curve. Now are they matching? Are the two curves matching?
No, sir.
No, it is not matching because this is a straight line, straight vertical line, but this is a slope. Again, now second approximation failed. So now I'll just summarize the second approximation. In second approximation, what they told was, since the battery is opposing the current from the diode until 0.7 or 0.3 volt, the battery is going to behave as an, diode is going to oppose the voltage of the current from the battery until the battery voltage becomes greater than 0.7 or 0.3. That means the diode is going to have an inbuilt voltage of 0.7, fixed voltage of 0.7 or 0.3, so which can be compared with a battery. So when your input voltage becomes greater than this fixed voltage what the diode is having, then the current can pass through it. Otherwise, the current will not flow. Under reverse bias condition, since we assume the diode will be in open switch condition because of reverse bias condition, the current will not flow, the current will be zero. But in forward bias, when your input becomes greater than the voltage of this battery, that is inbuilt battery of diode, so you will be getting. But still, when they compare the second approximation, that was a slope, but this was a straight line. So again, this got failed. Then next, they came, they thought of, and the third approximation came into picture. So this is known as third approximation, or this is also known as piecewise linear characteristics. So now first we'll understand why they're calling by the name piecewise linear. They are calling by the name piecewise linear because in order to prove or in order to provide the mathematical proof for this particular circuit which is designed, they used piecewise linear equations. Piecewise linear equations. These are all the mathematical equations. So piecewise linear equations were used to prove the obtained circuit. That's why the name is known as piecewise linear characteristics or piecewise linear approximation model. Because in electronics or in any sort of in engineering, whatever you tell, you should have a mathematical background for that, mathematical proof for that. So here they used piecewise linear equations to prove it. So that's why the name came as piecewise linear equations. Come. So now coming to the circuit. So what they thought is, yes, there is a slope. Slope, we know that slope will always come when there is a resistance. We know that slope and resistance are inversely proportional to each other. So if there is a resistance, then only the curve can have a slope. From this, what they assumed is, diode is not only having a battery and an ideal diode, it is also having an inbuilt resistance. It is having an inbuilt resistance. That inbuilt resistance is taken as RF, forward resistance, VK. This is the battery. This was the new circuit or the third approximation circuit. So according to this third approximation circuit, what they did is, so already we have a battery. How much this battery provides? Suppose it is a silicon. So how much, till what voltage it will not allow the current to pass through?
0.7.
0.7. So what they did is till 0.7 they marked the current as 0. So this is IF, VF, this is minus VR, that is reverse voltage. After that the current is passing through this, and since you have a resistance, the linearity will come into picture and slowly the curve came like this. Now when the current is, this is fine, so current is passing through this becomes a closed switch and current will pass, you got the result. But what if the current is flowing in opposite direction? Diode, what happens to the diode? What happens to the diode? Under reverse bias condition, instead of passing the current like this, if you are passing the current in this direction, what happens to this diode? That is, this is an ideal diode which is acting like a switch, no?
Open switch.
Open switch.
It's open.
The diode is acting like open switch. So when this is opening, no current will flow. Okay, so still they assumed in this model also, they assumed that in reverse, when a reverse voltage is applied, no current will flow. But when you compare these characteristics, are they matching with our practical characteristics, at least to an extent?
Yes, sir.
So they are almost matching. So the third approximation worked out under forward bias condition. But reverse bias condition, the third approximation didn't satisfy. So after this, we are having actually the fourth approximation. This is not there in our syllabus, so that's why we are not touching that. So what they'll do is just they'll add one resistor and they'll prove it. So when it is not there, let us not worry much about that. So so now in the third approximation, what we did, since there was a linear slope, we introduced a forward resistance RF to the battery, along with the battery and ideal diode. So this gave an almost the same curve which was matching with our practical curve. So this is piecewise linear approximation, third piecewise linear approximation. So after this, the next one is diode DC equivalent circuit. Diode DC equivalent circuit. There are, see, DC equivalent circuit as well as AC equivalent circuit. They'll ask you, this is a very simple question. Write the diode DC equivalent circuit. It will be for 1 or 2 marks. Simple one. Diode DC equivalent circuit means you should write one resistor, one battery, and one ideal diode. So what is an ideal diode? What is an ideal diode?
Which behaves as closed switch in forward current and
Yes.
forward bias, and open switch in reverse biased.
Yes, very good. So this is the equivalent circuit for DC equivalent circuit. Then what is the difference between this DC equivalent circuit and AC equivalent circuit? See, in AC equivalent circuit, along with this, what you'll have is you'll use a capacitor. We'll study that AC equivalent circuit in the upcoming topics. What we'll use is capacitor. Now you might get one thing, why we are not using capacitor in DC, why we use capacitor in AC? Because remember this, capacitor will always block DC signal and allows AC signal. Capacitor blocks the DC, allows AC. So if you use capacitor in DC also, it will not allow the current to pass through it. It will block it. Blocking in the sense it starts storing the charge. It will not allow to pass through. Suppose you have a capacitor like this, and if you are passing the current, then this capacitor will not allow the current to come here. It will start storing the charge. But if you are allowing an AC signal to pass through this, then the capacitor will not, the capacitor cannot charge by using AC. Alternating current cannot be used to charge a capacitor. So during that time, it will just act like a short circuit and it will allow the current. But the capacitor will charge whenever a DC signal is being given. That's why we tell the DC signal gets blocked. Block means what? Store, right? So capacitor blocks DC, allows AC. So that is the AC and DC sequences. So that's why we are not introducing the capacitor here. So equivalent circuit, basically how we define this equivalent circuit is equivalent circuit of a device is a circuit representing its internal behavior. Yesterday we were discussing a robot and a human being. It is going to tell how actually it behaves and all, but it is not actually a human being. In the same way here, we are going to make this equivalent circuit because we want to study the internal behavior. See, after going on to the approximation, we came to know that diode is having internal resistance, diode is having internal battery kind of thing, and diode is acting like a switch. See, so many things we came to know when we tried to write an equivalent circuit. Okay, so this is the importance of equivalent circuit. This is very necessary for in the design. So to design, you should know what actually it contains. Then we can analyze it and we can think on how we can change it, and even in your mechanical field also, if you know what kind of material you are working on, so then you'll be able to design, or you will be able to change the composition, and based on that you can plan your design, and you can decide whether this material can be utilized for my application or not. If you don't know the internal behavior, how it behaves, so it is not it's not so easy to apply it to the practical purpose. So now coming back to this, so equivalent circuit is a circuit which is going to represent the internal behavior of the device. Next, after this, we are having DC load line. We are having DC load line. So what is this DC load line? DC load line is the graphical analysis of a diode circuit which gives precise levels of voltage and current. I have a device, but I should know to what is the maximum extent of voltage and current it can withstand. So that is being drawn by DC load line. So in the DC load line, what we are going to do is the same VI characteristics we are going to take. This is the voltage, current. We have a VI characteristics like this, and what we do is we take one point along V, we take a point along I, and we are going to join them. The point where both the VI characteristics and the DC load line are going to meet, it is known as Q point. It is known as Q point. Also, it is known as operating point, or this is also known as quiescent point. Okay, this is the maximum current. This is the maximum voltage. This is the operating voltage and current. So if you get this point, just draw the vertical and horizontal lines. This point, whatever you are having, no, this is our operating current. This is our operating voltage. So now, why we need this, or what is the difference between this? Maximum current means that is the maximum current our DC load line can give. That is the maximum current that is the maximum current that the diode can withstand or diode can allow. What is maximum voltage? That is the maximum voltage that diode can withstand. Then what is this operating current and operating voltage? This operating current, operating voltage is the actual working voltage and current right now. If you want to know right now at what voltage and current my diode is working, that is the operating voltage and current. You might have the range of maximum voltage, maximum current, but it doesn't mean that it should be always at the maximum voltage, maximum current. It might be working at any point, any level. So that gives you the present working voltage and current. But this gives you precise voltage and current, that is maximum voltage and current it can withstand. Okay, so now the question is, yes, we are fine with this. So now how we will come to know that this itself is the point and this itself is the point. Okay, this is a VI characteristics we obtain by just knowing the diode behavior, or by doing some experiment we'll come to know this. We can plot this graph, but how we will come to know that this is the point and this is the point? For that, what we'll do is we'll take an example and the example of a circuit and we'll analyze. So for this we have a battery which is connected to a resistor, a diode, this is the battery. Let us take this is 5 volt, a resistor which is having 100 ohm, and this is the forward voltage drop of the diode. Now, in order to find the current, this current and this voltage, what we need to do is, because this is our forward voltage, this is our forward current. To know this, what we need to do is we need to apply Kirchhoff voltage law, KVL, Kirchhoff voltage law. So in Kirchhoff voltage law, what we do is we are going to apply from negative to the positive, or if you want you can apply from positive to negative, any way you can do. Always remember, whenever the current or the loop is moving from negative to positive, then you should take positive value, positive sign. if your loop is moving from positive to negative, then it will be taking negative. Now the question is, fine, for this is the positive, this is negative, for this is negative, this is positive, fine. Then you can ask me what you will do for this, because resistor doesn't have polarity. So what I should do for that? So always for resistor, what you should do is the entering point, you should take the entering point as positive and leaving point as negative. Entering point is what? This one. Leaving point is this one. So the point where the current enters, or the terminal where the current enters, that is positive. The terminal where the current leaves, that is negative. Okay. Now we'll start from this point. Minus to plus E. After that, I have taken this clockwise direction. After that, it will move like this. So it will come here. When you are having this in Kirchhoff voltage law, what you should do is you have to represent equation either using voltage or by using I into R. You can use voltage directly or you can use I into R product. This is the method. So when coming here, you have a resistor, you cannot add only resistor. You should take, what you should take? What you should take? Can I add the resistor in the equation directly, or what I should take? Hello. What I should take? These are all you have already studied in your second PU or 12th. KVL, KCL. In Wheatstone Bridge problems and all. Can I take resistance directly in the equation, or I should take any of either current or voltage together in KVL?
Only voltage, sir.
I can take only voltage, or if you want to take
Current and
you should take current along with that. I don't know what is the voltage across resistor or voltage drop across resistor, but I know what is resistance. So that's why what we'll do is I'll take current into the resistance, and the current which is flowing here, that current I'll call it as IF. Now tell me what the sign I should use, whether positive or negative.
positive.
Positive. Look into this first and look into this.
Negative, sir.
Where it is leaving. I told you, entry point is positive, leaving point is negative. Plus to minus, if the loop is going from plus to minus, what you should get?
Negative.
Negative.
Negative, sir.
Now, this is the anode terminal. Anode is positive or negative? Anode is positive or negative? Positive. Cathode is negative. Now tell me, when the current is flowing through the diode, what symbol I should use? What symbol I should use?
Negative.
Negative. Plus to minus. So the current is moving like this. Plus to minus, minus. See, these things are all not there in the textbook. These are all the basic things you should remember. So better you can write anywhere. Plus to minus Vf is equal to 0. Now I want this point. This point is Vf. This point is If. If you want this point, what you should do is, if I want this point, just see to its horizontal position. What will be the value of current at this particular point? What is the value of current? See the graph. It is a very minimum basic I'm asking. At this particular point, what will be your current? If voltage is Vf here, what will be your current? Just see at the y-axis. What do you have at y-axis? 0, no. Coordinate geometry. If you have a point along x-axis, what will be its y?
0, sir.
0, x comma 0. If you have a point along y, then what is its
0,
coordinate?
y.
0, y. The same thing is here also the same thing. At this particular point, if you want to take Vf, then If will be equal to 0. So when I substitute If is equal to 0 here, what happens? E minus 0 minus Vf is equal to 0. That is equal to E is equal to Vf. What is the value of E? 5 volt. That means Vf is 5. So this is 5 volt. In the same way, if I want this point, what will be the Vf value? At this point, which is on y-axis, what
0.
is the so Vf will be equal to 0. E minus If into R minus 0 is equal to 0. I want the equation for If. So If will be equal to E by R. This is E by R, this point. So by using this formula, you'll find this point. By using this, you'll find this point, and you are going to join. This is how you are going to find the DC load line. Based